Now let's move to our next speaker, an engineer from biomechatronics and efficient energetics at ITMO ENR. Ivan Ninakhov will do the introductory master class into deep learning. So you need to know the concept of deep learning, the basic level of programming in Python and knowing the command row. Over to Ivan. I hope it's utmostly exciting. Hello, I'm Ivan Ninakhov. I'm learning for master at ITMO, and I also work at the laboratory of biomechatronics and bioenergetic robotics. I will talk today about the deep learning tools for classifying images and about for adaptive object recognition. My talk will have two parts. I will start with introduction to Google Colaboratory. Then I will talk about the main framework for using with deep learning of PyTorch. And then I will tell you about metric learning for classification tasks with changing set of classes. Let's proceed to Google Colaboratory. If you can notice, it's a Google service for research and educational purposes. It's free, absolutely free, and it provides us the calculating capacity at Google servers. You can see it as a remote computer for Linux with the main libraries and tools for machine learning selected. And the interaction goes on with code blocks for laptops. So those code blocks you can add independently for actions during the current session. So each the laptop and iPad, they support the basic Linux functions for access to file navigation, assessment of the system state, but the most particular side for deep learning, machine learning is access to GPU. And so there is the execution environment. You need to click it and to select GPU. So our session will reload. Or what's this? The session will reload, and we will get information about our graphic processing unit. So we have 11 gigabytes of memory we can use for training our networks. Also, a useful property is that if you make a mistake in a code on your local PC, that leads to memory leaks and producing lists of a huge size, and then your RAM will be over and your computer will hang up forever. Here the session will just reload with the error that out of memory. Also, here in Google, you have in Google Cloud, you have integration with Google Drive. You need to import a library, select a folder where you will install your Google Disk and run the function using for assembly. For this function, you will have to authorize yourself in Google and allow access to your Google Disk and install generated key into the row. Now we can see our Google Drive as a folder on a remote PC, and we can execute all operations with the files. You can see them here. And the most often goal is access to data sets. And as Google has limitations for downloading files from Google Drive, it's most reasonable not to contact Google Disk or to minimize the amount of downloading operations. And it's reasonable if you have a data set as an archive to copy it once to a remote PC. You can access from your Google Disk and work with this archive, unpacking it. If a data set supports the direct link, it makes sense to use it. Avoiding Google Disk, for that you have wget command and unzip to avoid repetition when downloading these same objects. Also, Google Colab can unload and process images from your camera. And in a tutorial, you can find this information. And you see almost all the files are already unzipped. And now let's move to PyTorch library. You might know that the training of neural networks is connected with calculating gradients for every weight, with excluding errors and updating the values. PyTorch, in its foundation, executes all these low-level operations the way that we don't need to care about this. And apart from that, above that, PyTorch has a lot of tools to work with deep learning, like functions for preparing data for learning, sets of main deep learning layers, a set of optimizers that set the rules, weights, loss functions that respond to our gradients, and sets of tools to monitor your code and execution time. By calculation time and so on. Also, here you see like the tool, the set of tools to import models you already trained to other devices, mobile devices, also embedded devices, controllers, and so on. Let's move to the task we will try to solve during this, while I will be talking. We will classify objects from the data set called Tech256 I just downloaded. To accelerate code operation, we will classify just 5 objects. The data set includes several thousands of objects, which represent 256 classes and one background class. For the beginning, we need to prepare our data for training in the neural network. Deep learning model in PyTorch, they expect not only image, but a massive from a set of such images. So the model wants to get a tensor built by PyTorch, and the shape, it means the number of images in a set, the height, the width, and the number of channels. Also, we need to have a meta class vector that would show which is the class of the object. For such purposes, in PyTorch, you have different classes, including the data loader. A data set is an abstract class that you need to investigate and create a new class for data sets, where you need to implement 3 functions. You need to initialize, indicating dataset parameters. You need to implement the function of getting the object, and the function for reproducing the length of the dataset based on its objects. Let's go step by step, and I would like to tell you that implementing all the 3 functions can be done by a number of ways. There is a countless amount, but I would tell you about those that appear the most convenient to me. Those I use in my research work. So as an argument, let's see the folder where our data set is like the transformation you need to do with the image to offer it the shape it needs, and we need to show if it's for training or for modeling, because to evaluate the model you need to use different data. So we will divide our data set into training part and other modeling part, iteration. To get access to our objects, let's browse all the folders we indicated here. So for all files that are images, we will find their class. Let's see that the object class is indicated in their respective folders. And before the dot, you have the index, and then the text description of the class. And you have images inside those classes. So you can get a class dividing our folder by a dot, and you get an element. Then we would filter our images by those that only belong to our narrow classes. So randomly, I selected 5 classes just to minimize the size of the data set. Then we can save our paths to the file and labels of the class. After the integration, we get 2 lists. One of them will show, will indicate files with images, and the next one, class labels. Now we need to split or divide our data set, if it's for training or if it's for validation. So we need functions learn and train test split, they would take two identical data array. It will split according to what we plan. 80% of them would be for training, and 20% for validation. We will also explicitly set the number of random number generator. It's important to split the code in one and the same way. It's important for reproducing the results of the experiments, and the best practice is to show that state. After we divide the data sets into two parts, we see the argument sent to our function, and based on that, we reduce our lists based on this solution. So also, during the learning, we need to have a class label, and the label should be an integer. But classes are represented as rows here, and in a general case, there is an algorithm, label encoder function, which is part of the same library, and that transforms our row representations into the form of numbers. And at the end, we see the size of our data set. And let's move to the function. A data set should return the object itself and its label, its class. We need to read the image first. We use CV function. That's the most popular library for working with computer vision. We will read the value. We would get an element from our list, an object by index. If we have any transforms, we would change our image based on those transforms. And then we get the class label from our list of encoded labels. And then we return the data array of two elements. And finally, we implement the function of dataset length that can be implemented as our array with self image files. Let's create an object and take an element, get it label, and show and retract the image represented in this dataset. I would like to remind you that the class label now is an actual number, and to get a text from it, you need to do the reverse transform with the same label encoder, where we will supply a list consisting of just one element, and then we would go back and we will return just the first element, because it is a list of just one element. And just to get rid of the list, let's take the first element. As you see, the class label corresponds with the image. And let's continue with the transformation. The transformation transforms the image, and they serve for different purposes for augmentation of data. Augmentation is transformation when the image is changed, but the class is not. So we can reflect it using the vertical axis and get a new image of a frog, and the class will remain the same. And we can use a different number of filters, apply them, change colors to some extent, rotate the image. We can add the perspective, but the place of class will remain the same.
We can take a new image, and the new image is going to be perceived as another new object. And it's a great way to artificially increase the data set. Transformations that augment the image must receive objects type BIL. It's a library to work with images. We're going to discuss it now. First of all, let us transform our dataset into this PIL image, and then we will apply all our transformation for augmentations. And with a certain probability, these augmentations will do some transformations. The second application of transformation is to bring our image in line with neural network requirements. First of all, we need to get tensors to enter the neural network. In order to do that, we run function to tensor. In the majority of cases, we need to obtain the image of a fixed size. In order to do that, we use the function resize. And in case of a pre-trained image network on the dataset ImageNet. Dataset ImageNet is one of the largest datasets. It has millions of images that have thousands of classes and classes of categories, and it is used as a popular dataset for comparison of different state-of-the-art models, the newest, the best, the most powerful models. And it's used for pre-training of models. If we use a pre-trained model, if the model was pre-trained on this kind of data set, that we need to specifically normalize our images. For ImageNet dataset, we calculated statistics where we found average of every mean of every measurement and standard deviation from every value. And the article says that normalizing images this way to these size will improve the quality of neural network performance. Now let's create two objects of this according to this data set with our transformations. One of them is going to be validation, and the other one is going to be a training one. We see that one has 4 images and the other has 100 images because we split 70 to 30%. We split them in this ratio. And then, if you remember, we need to obtain not just one image, but we need to receive batches of images. In order to do so, there's a data loader function. It collects our images into batches, a few images in every batch, and size of images in the batch and the numbers, it is specified at this stage. You can do it when you need it. So during the training process, we will not upload all the data set into the memory, but so that we do it step by step. Step by step, the data set will be downloading only those parts that we are going to be using to train the network exactly at this point in time, and not the whole huge data set. Now, after having initialized our data set, our reference, now let's build the model. All models in PyTorch must follow an module which has a low-level description and logic of deep learning models management. We need to initialize it in the root, and we need to indicate how our neural network should process the input images. In this case, we are going to create a consequent sequential neural network that will consist of full-size layers and average pooling a layer in the middle. You should know that during classification, the size of the output layer is equal to the number of classes among which we need to recognize objects. So we need to submit this as a parameter into our function. Also, just for the sake of an example, let us set parameters of layers as arguments of our initialization function. Just a few words about how layers are created in our neural network. The majority of layers where you do some complex operations such as folding or full-size layers, fully connected layers. In the beginning, they have the input size of the vector, full size, the input size of the tensor. In this case, we have 3 because we have 3 channels because it has colors. And let's say that the output size is going to equal to 16. It means that we're going to have 16 connecting layers on every layer. The size of the kernel, it's 3 by 3, and padding equals to 1 so that the image size remains unchanged. Thus, after having gone through these folding layers, we will have a tensor with 220 batch size multiplied by 224 multiplied by 32. Then we apply average pooling layer, which will reduce our spatial size by 2-fold. By the factor of 2, is going to reduce it by the factor of 2. As a result, we're going to have this size, which is going to be an input size for a fully connected layer. Before submitting our tensor into full connection layer, we need to unfold our tensor that is multi-size, massive, into a vector so that it's one size mass. After setting the main layers of the network, let us set how the signal must be processed. Having some massive at the end, at the input, we submit it to our features extractor. Oftentimes, we can see this description and this datation when folder layers are named feature extractors, and classifying layers that consist of fully connected layers are called classifier. The input tensor is put into feature extractor. We obtain some features, and then we do classifications. We use classifier, then we return our data set with the size and with the number of images per batch multiplied by the number of classes. So it's going to be 2 columns and 2 rows matrix. Oftentimes, we use pre-trained neural networks, since training from scratch and applying all these filters and fully connected layers, it takes a lot of time, and you need to process huge data sets. And it makes more sense to apply pre-trained models that most probably have optimal architecture. It had been installed on them, and they had demonstrated their efficiency in different tasks. And there's a library for that, Torch Vision it's called, and it's a part of PyTorch library that has a set of pre-trained models and architectures. We import a MobileNet architecture, just for an example, and we indicate here that it's going to be training, pre-trained. We say that it's pre-trained, that it had been pre-trained on the ImageNet dataset, and we download this dataset when we run the model. And as I said, ImageNet dataset has 1,000 of classes, so output size of the last layer in pre-trained networks equals to 1,000. And we need to change the last layer to make sure that its size is the same as the number of our classes. In order to do so, we find the number of our classes on the dataset, and we change the last layer of the network. We replace it with our new one. We keep the input size. We only change the number of classes on the dataset. Now let's train the model. To begin with, let us set the values for random number generators. Let's set the number of epochs, how many times we train the model on our data set. So how many times we are going to put all the data set through our model. Now, in order to use the video card, we need to transfer our objects to video card. We make sure that the video card is available with the help of this command. And in case the video card is available, then we put here, we assign the device, we assign name to the device. CUDA is the name of a tool for low-level parallel computations on video cards in this shape, in this way. And it's applied as a signal. It signals that our tensor is on the video card or another object is on the video card. Then we put our model that we had downloaded onto the video card. Now we need to set the optimizer and loss function. Optimizer, let me remind you, optimizer is the function which dictates the rule according to which we adjust weights in accordance with our ingredients. And the loss function is a function that we're trying to minimize during the training process. Let us set the training function. During the number of epochs, we're going to have two phases, two runs, like two phases. First phase is train, and the second phase is validation. During train, we indicate the type and the mode in which our neural network is going to work. We need to do that. It is necessary because there are some layers that work different ways depending on whether the model is trainable or whether it works as a predictor. Then we go through all our data load, which collects all our images and labels into batches and supplies them and feeds them step by step by batches. Then, since operations on objects must be done on the same device, we need to put it onto our video card as well. Here is neural network features. We calculate loss function. We sum it up so that we can get the total loss function. Now we need to update the weights. In order to update the weights, we put our all gradients to 0. We optimize them to 0. We do backward propagation of error and optimize it again. After we go through the whole data set, we need to assess our model. In order to evaluate it, we switch it to eval mode, evaluation mode or validation mode. This is the mode in which neural networks is already working. It's already predicting some data. It's called inference. And this term is also well known. It's a well-established term. By default, when we operate on tensors in PyTorch, the information is stored, the information about gradient is memorized here as well, so that we can further distribute error. But in inference, we don't need it. This is why we switched it off. And first of all, it will speed up the process of evaluation. And second, it will reduce the amount of memory that we need for this. We go through the whole data set again. We transfer our images, batches of our images, to the video card. We relocate them there. We do prediction. In the output, after predictions, we will have a double two-dimensional tensor multiplied by the number of classes. So in this case, it's these numbers are in the screen, where for these images, you will have some of the elements, and the largest value of the vector will be in line with the most probable class of the object. In order to do so, we use our argmax function, which chooses the largest element on the first axis. Then we compare our predictions with real-world data of classes, and we sum them up and put them into overall correctly predicted classes. Then we calculate accuracy, and we derive the metric. This operation is repeated 20 times by the number of epochs. And now let's have a look at the trend of loss function and accuracy. As you can see, 7 epochs have been done already, and loss function is going down, which means that the training process is going well and our accuracy is improving. Let us have this option. Let us, the process is obvious. I don't think we need to continue. So let's assume that we have finished the training of our network, and we need to save information somehow and have a chance to use them later. The best practice is not to save the model itself, but to save the state of the model, the state of its parameters. You can do it with the help of torch save function, and then you can load it with the help of torch load function. In order to do that, we might need our Google Drive again. We can save there our checkpoints to our Google Drive. Saving Google Drives, well, it's useful to do it after every epoch or with a preset interval. In order to download the pre-saved, in order to upload the pre-saved weights, we create the same object with the same architecture that we had previously, and we assign the weights and we assign new parameters to them. And now I'd like to tell you about 2 settings on PyTorch that will speed up the process, that will speed up the training of the neural network. A Catalyst library is used here to automate some routine actions. We need to notice that epoch iteration functions will be the same for all models. Quality evaluation function will be very similar for the majority of models. And in all the process, there are very few places. There are a lot of places that are very similar or identical in every experiment, and Catalyst optimizes this process. It's not pre-installed by Google, so you need to install it manually. And without going into details of the code, I will just show you here that the same training process that we wrote by hand can actually be implemented with the help of the Catalyst, and you just suppress the code and you improve its legibility and clarity.
The Catalyst library as well supports changes in different parts of our learning process. If you need to change anything during your project, and it's very handy and convenient, and you can use different optimizers, metrics, evaluate the quality of models differently, and write about experiments. During the last run, it was a learning process. The learning took long, but accuracy went up, and the process went as it should be. The second library is called Optuna. It's used for optimization our parameters. Let's have a look at our objects we used for training. First of all, we indicated the optimizer, stochastic gradient descent. We set the learning rate, but it's not clear if the parameters are the best for your learning. It's not sure that the loss rate would be optimal, and also sizes, kernels of your layers were selected in the best possible way, and also you need to set the languages. Hyperparameters are parameters set before the learning, and they do not change, and Optuna optimizes them, adding just some bits to the code, and it allows to change different hyperparameters in our learning process. It should be noticed that the most part of the code remains the same, and we only add two variables that are the target hyperparameters for us. Then we utilize for and optimize the learning rate and the batch size, because it influences the learning process. As you can see, by adding just a few rows, well, and I won't go into deep details here because it is in tutorials for the library. It supports a lot of algorithms for searching optimal parameters, and records data on all experiments. And to end my first part, I would also like to show you the library called weights and biases. You can generate it in Google Colab. Imagine that you make an experiment. You train a model. You have a loss function which changes over time, and you want to monitor, you want to control the trend. Weights and biases allows you to create accounts where you will be given some space on their server, and you can unload their data on your learning process. Once you install the library, you import it to Python, initialize it in your code, indicating the name of the project and experiment name. And the project is a set of experiments that serve to one and the same goal, but with a different hyperparameters. If you have a process, some learning, you can download there some data using log function. You need to set the target value and the variable, and at what learning step it was done. By default, during the first launch, the first initialization, you will be requested an authorization. You will have to authorize yourself at weights and biases and get connected to your account, like when you were importing your own Google Drive. After the experiment is over, you can go through the website, weights and biases, and go into an experiment called a sample project you just created. You can see all our experiments in this project. Compare the graphs, the curves. You can compare time, runtime, and other parameters, other properties for each and every experiment. Yeah. Also, there is information was added to the terminal, information on CPU, on the system. You see if your computer hanged up on some of the experiments, and many functions for visualization of your process. On top of that, as all the information is stored on weights and biases service, you can get access to your experiments from whatever computer you want, and they will not be deleted once your session will be finished. Okay. Enough for PyTorch. Now the next part, metric learning. It's more theoretical part. And for beginning, let's take a task related to face recognition. How can you recognize face? You can train a neural network to be focused on a preset type of classes, but if there is another person added, you will have to retrain the neural network. And if there is a person, if you no longer need to recognize a person, then there is no need to recognize the class. So the classical approach to classification problems is not rational here, and we need to look for other approaches. Also, we want to compare similarity of objects to do the tracking for different frames in a video stream. Also, there is a multitude of tasks and problems where you cannot use standard approaches for classification, and metric learning caters for these goals. So have a look at the classical standard classification. So we have a number of classes, and we train a neural network to project images on vectors with n numbers, where one number, as we would try, would be equal to 1 and the other to 0. So the probability of identifying one class would be 100%. If we do it differently, we can take our neural networks as a function that would project images on like an n-dimensional space. Imagine we have two classes. Then the neural network will project our image on a plane surface, and when we get a classification, we would tend that objects of one class would be close to one axis and far away from the other, and the same with the vector of the other class. If n equals to 3, Then we have like another axis perpendicular to those two, and we will have a three-dimensional space. If we add more classes, then we would have a multiple space, and vectors would be perpendicular in the same way. So the neural network takes our dots, our vectors to a certain space, and how can we use it? We can project dots to that space and compare them, finding distances between them based on the similarities. But we need a different rule for projection and training the neural network. So, and this parameter is loss function. In metric learning, the main function is the triplet loss function that takes three objects, the basic, the positive, and the negative. So the negative would be different from the basic. And during the process of learning, the neural network tries to keep the distance between the basic and the positive minimum, and the basic and the neutral as big as possible. So when we would train the neural network, doing it for similar tasks, we would have a network that would group similar objects. Because, as a matter of fact, objects which are visually similar, they belong to one and the same class. So to present the objects, so they will be close one to the other. If we take a dataset with such representations, with a class label, if we do representation of a new object, then we can classify it, finding the closest neighbors to it. It's called the K nearest neighbors method. And if K is fixed, we set it, well, let's imagine K is 3. So if the target point is the triangle, and we are looking for the nearest object, so it's quite probable that it would be a purple circle in this case. What's the plus of this approach? We can add or remove objects from our data sets. We are not linked to any type of classes. And for classification, for a good classification, you need much smaller sizes of a data set compared to a classical one. Yeah, there are also disadvantages of this approach, because compared to a standard classification, quality and accuracy of classification are much lower. And if we have really large data sets and many classes, so the search for the nearest neighbors would take long. Let me show you the way it works. We have like coil store data set with 5,000 data set, well, about 100 objects, 72 images per object. Let's download it from the website, unzip it, and like in previous cases, we'll write the class over the dataset to create the access logics, the logics for accessing the dataset. And then we will use a pre-trained model based on transformers from Facebook that creates projections of our objects for 600 for a multidimensional space. So we indicate transformers, data loaders. We download the model with Torch Hub. Then we move it to GPU. They take the inference mode, and we move all across the data set and store vectors we obtained, vectors from our model. For that, we create two empty tensors. Let's create them on GPU to accelerate the process of operations with them and do the iteration without using gradients. So getting the attributes, vectors for the batch, we add them to those that were to the data array created before. We do the same with the class labels, and then we would train our classifier of k nearest numbers on the new data set we obtained. Let's also split the data set for that. I will show it. You take the code, we iterate it object by object. You can see that we use TQDM library to create nice-looking crossbars that don't overload data transfer. Then we get the vectors, so we will split the data set into two parts, and we will notice that we will use 20% of images for training and 80% of images for testing. And then we'll demonstrate the quality of work. So the number of nearest neighbors will be 10. We will train the model. For the training part, we will do the prediction, and we will find the matrix of errors. The error matrix is approximate, where on one axis you have predicted classes, the number of objects classified as predicted, and on the other axis you have objects that correspond to the actual real class. So if you see the diagonal of the matrix, you see a correctly predicted object. We will also find the accuracy using the diagonal elements of the matrix, and we will see the mean, the average meanings for every class. And we arrive at 95%, although we only used 20% from the data set, and we had 14 images per class. And finally, I will show you how our attributes are distributed across the space. It's not possible to visualize such a space, but you can put it on a two-dimensional plane surface. There is like UMap algorithms and UMapLearn library for visualization of such a project. We would transform our data and take the graphic information. And it's clear that objects of the same class are highlighted with one and the same color, and they are clearly different from others, except for some special cases. And this graph shows and proves high accuracy of classification. That classification is not ideal in our model. And it should be noted that when we select a higher size for test sampling, the accuracy will also go up to 90%. I'm done here. Thank you. Thank you for your attention. If you have any questions or the need to share with you the laptop, well, feel free to write.
Спасибо, Спасибо, Иван.
Thank you, Ivan. Thank you very much.